All right, let's talk about dividing exponents. So we're going to again start out by putting it into factored form. So when we have x to the fifth divided by x to the third, we have 5x's in the numerator. So x times x times x times x times x. And in our denominator, we have x to the third, so x times x times x. Now, we have to think about what we know about fractions, especially when we have fractions that have the same thing in the numerator and the denominator. So, for example, if I isolate these two x's, we have one in the numerator, one in the denominator, and if we notice, they're the same variable. So if we have x divided by x, no matter what that number is, the answer will always be 1. So what I've really made here is a 1. And we have another one and another one. So basically we're just taking pairs of the same variable in the numerator and in the denominator, and we're going to figure out what we have left. So we removed 3 from the numerator, 3 from the denominator, and I have 2 x's left, and those 2 x's are in the numerator. So my answer is x to the power of 2. We could put x to the power of 2 over 1 because technically what's left on the bottom is 1. Because this is 1, 1, and 1, so that's like having 1 times 1 times 1, which is 1. But I don't actually need that there. This is my simplified answer, but it does mean the same if you have a denominator of 1. The next one, got a few more terms to it, a little bit more. So we have a to the fourth power multiplied by b to the second power divided by a times b to the second power. So again, starting out with a fraction, because in the numerator we have a times a times a times a. We have 4 of them multiplied by b to the second power, so b times b. Then in my denominator, I have a, just one of them, because we have the exponent 2 here is only attached to the b unless it's in parentheses like that. Then it would be both of them. But our exponent's only attached to that b, so technically there's only one a multiplied by b times b. So again, I want to take away any of the any of the variables that I have in both the numerator and the denominator. So I have that a and a there, and then I have b over b and b over b. So I've made all of the ones that I can make, and I am left with a to the third power, because I have 1, 2, 3 a's left, and then nothing in the denominator, so 1 or just a to the power of 3. Now, we have one over here. This one is h to the second power divided by h to the fourth power. So, again, drawing my fraction bar, I have h times h in my numerator, and in the denominator 4 of them. H times h times h times h. All right, perfect. Once again, I'm going to make my ones. I've got there and there. And then this time, my answer is a little bit different. We have h squared, but this time they're in the denominator instead of in the numerator. So my h to the second power goes in the denominator, and I have to put a 1 in the numerator. So 1 over h to the second power. Now, what does this look like? If we're thinking about the rule, if we don't want to take our whole problem and expand it out into factored form, maybe the exponents are just too big, maybe we just want a shortcut. So, if we go back and look, we had, looking specifically at our exponents, we have 5 and 3, and our answer had an exponent of 2. Over here, we had 2 and 2, and there was none left. So technically, b to the power of 0, which is 1. Because when we had b to the power of 2 over b to the power of 2, we had the same thing in the numerator and the same thing in the denominator. So technically, that's equal to 1 whole, but an exponent of 0. And then we had a to the power of 4, and then technically we can say this is a 1, and that ended up as a 3. Now I don't want to confuse you. We would write it as a to the power of 3. So, 5 and 3, 2, 4 and 1, 3, 2 and 2, 0. So technically what we are doing is we are taking the exponent in our numerator, a, and subtracting the exponent in our denominator, in this case, b. So, let's see how that works. This one, we have x to the 5th, x to the 3rd, so this is x to the 5 minus 3, which is x to the second power, which is what we got. Over here, we have to do this twice. So we have a to the power of 4 minus 1, b to the power multiplied by b to the power of 2 minus 2. So a to the power of 4 minus 1 is 3, b to the power of 2 minus 2 is 0. So we simplify that to a to the power of 3, because this is equivalent to 1. All right, then this last one, this is where it's a little bit different. We have h to the power of 2 minus 4, because the 2 is our numerator, the 4 was our denominator. So this one is actually h to the power of negative 2. And we know that this problem is a little bit different by our negative exponent there, but also by the fact that those two h's ended up in our denominator. So what this means is what we have coming up next, which is our negative exponents. When we have a negative exponent, it's going to go into the denominator of a fraction, just like we did over here. All right, let's now take a look at negative exponents and what those mean. All right, when we see x to the power of negative 4, technically, we are going to draw ourselves a fraction bar. And when we see that negative exponent, we're going to think, if it's not in a fraction, we could write it as x to the power of negative 4 over 1. And we're going to put any negatives into the denominator. So this becomes x times x times x times x. Those are going into the denominator. And then, since there's nothing in the numerator, we can put a 1 there. So 1 over x to the power of negative 4. Now, the same works for this one, except for in this one, our starting point is a to the power of negative 3. 1 over a to the power of negative 3. It's already in the denominator. So this time, we are going to take those and we're going to move them to the numerator. So we have 3a's, and then we're going to have a denominator of 1. Now, I forgot to simplify here. When we are working with exponents, our goal should always be to get rid of the negative exponent. So when we're asked to simplify, when we're asked to evaluate or to solve or to use the laws of exponents, we want to get rid of those negatives. So our simplified answer without negative exponents here is going to be 1 over x to the power of 4. Since we switched them into the denominator, we flipped them, they are no longer going to have a negative exponent. And then same with over here, this 1 over a to the power of negative 3 is going to become a to the power of positive 3 over 1. But again, we don't need the denominator. We can just say a to the power of positive 3. Okay, now we're going to use that rule as these become a little bit more complicated. We're going to look here. B to the power of negative 4 divided by c to the power of negative 6. Now, I do want to mention here that we do have different bases. We have b and c. So I'm going to start by drawing my fraction bar. I know that since this negative 4 is the exponent and it's in the numerator, it's actually going to move down to the denominator, and my 4 b's are going to go there. And we're looking here. We have c to the power of negative 6, and that negative 6 is in the denominator, so we are going to flip it, and it's going to go to the numerator. So my 6 c's are going to go into the numerator. 1, 2, 3, 4, 5, 6. So my simplified answer, I've already taken care of the negatives. We switched them out. So I have c to the power of positive 6 divided by b to the power of positive 4. Can't simplify anymore because my bases are not the same. So that is my simplified answer. Over here, I'm going to start by drawing my fraction bar, and I'm going to take care of what's on the top. So this f to the power of negative 4 is going to flip down to the bottom. I'm going to have my 4 f's down there. This g to the power of positive 7 is going to stay where it's at. So g times g, 7 times 5, 6, 7. And then this one, my g to the power of negative 3. Now that negative 3 is in the denominator, so it's going to flip and go into the numerator. So I'm going to add 3 more g's up there. And then h to the power of positive 5 is in the denominator. It's positive, so it's going to stay where it's at. I'm going to add my 5 h's to the denominator. Now, looking here, I don't have anything that's in both the numerator and the denominator, so I can't make any 1's here. However, I can simplify all those g's because I had 7 g's and then I had the 3 g's from the bottom. So altogether, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 g's. So g to the power of 10 over, and then I have f to the power of 4. I have 4 of those, and h to the power of 5. Can't simplify any more than that. There's my final answer. So, thinking about those rules, whenever we see a negative exponent, we have to think about flipping it, making it a fraction. If it's not a fraction already, we're going to turn it into a fraction, and that is going to be x to the power of positive a in the denominator. So if it's x to the power of negative a, it becomes 1 over x to the power of positive a. And the same thing is true over here. If we have 1 over x to the power of negative b, we're going to take that negative, flip it into the opposite part of our fraction, and we have x to the power of positive b you could put over 1, but again, you don't need to. So those are our fraction or our exponent rules. One or two other things that you might want to keep in mind. Anytime you have an exponent like x to the power of 1 or g to the power of 1, it just means that I have one of those, so just x or just g. When we're talking about x to the power of 0 or anything to the power of 0, that answer will always be 1. So those are just a few extra little rules that we talked about along the way, but are also good to keep in mind as we are working with the laws of exponents.